Guests today, so I need your undivided attention. We're not going to chit chat with our friends next to us. We're going to give our utmost respect to our guest speaker, Dr. Greenberg. He's going to share with us about the nervous system. If you have a question, you can raise your hand. It's an interactive presentation. If you're chewing gum or eating candy right now, do me a favor and go throw it out. All right. Are we ready? Without further ado, Dr. Greenberg.
7th period, you're close to the end. So thank you guys for having me today. My name is Dr. Greenberg, and I'm a neurologist, work at the University of Texas Southwestern here in Dallas. And first, I want to give you a little introduction to what I do and what the world is like for neurosciences. So there are several different types of doctors and clinicians and scientists who work on the brain and the spinal cord and the nervous system. They're medical doctors who are neurologists and neurosurgeons. So the difference, one of the questions I get all the time is, do I go to the operating room? Do I operate on patients? That is a role for neurosurgeons. The neurologist takes care of patients outside of the operating room with a variety of different diseases of the brain or spinal cord. Can anyone here name a disease of the brain or the spinal cord? So scoliosis is a curvature of the spine that can affect the spinal cord.
Cerebral palsy.
So cerebral palsy is damage to motor neurons, so it makes it hard to move. Has anybody heard of Alzheimer's?
Yes.
Yep. So that's a neurology disease. Has anyone ever heard of a stroke?
Yes.
Has anybody ever heard of seizures?
Yes.
Autism? Schizophrenia. These are all brain-based diseases that would be cared for by a neurologist, sometimes a psychiatrist, and we all focus on the brain health. How do we keep healthy brains? Like preventing trauma, preventing accidents and concussions, and then how do we take care of brains once damage has been done? So I understand that you guys recently went through the nervous system. Is that correct?
Yes.
So raise your hand, tell me a couple things you remember from what you learned about the nervous system. Do you remember any of the cells that make up part of the nervous system? So what's a cell in the nervous system? What is it?
Nerve cell.
So a neuron or a nerve cell. And so what are some of the parts of the neuron? How do neurons talk to each other? What do they have? Yeah. So the axon, perfect. So the axon is the arm that goes out from the neuron to talk to the rest of the world. But what does the neuron have to hear those signals? What is it? Dendrites. So the dendrites are listening to the world and the axon's talking to the world. So your brain is made up of trillions of neurons that are interconnected, and they allow you to do everything you can do. Listen, see, smell, talk, move, run, jump, learn, remember things. It's all made up of networks of neurons. So can you guys remember, in terms of the human brain, any of the parts of the brain you learned? So what was it? So the cerebrum is the top part of the brain, and it has how many halves to it? How many parts to it? 2 halves, 2 hemispheres. What else?
Cerebellum.
So the cerebellum, the bottom part of the brain, responsible for what? Remember? Balance and coordination. Very good. What else? Brainstem, that bottom part of the brain, and what's that responsible for? Involuntary movement, like breathing and your blood pressure and pulse. What else?
Left hemisphere.
So the left hemisphere and then the right hemisphere.
It controls the right side of the body.
Left hemisphere controls the right side of the body and vice versa. Good. And then you guys remember the parts of the cerebrum, the parts of the upper part of the brain. There were 4, what are they called?
Lobes.
Lobes of the brain. Perfect. Who can name one of the lobes?
The frontal lobe.
Frontal lobe. So close. Occipital lobe. Great. Now there are 2 more, the frontal and the occipital. And what are the other 2 lobes of the brain? Say it again. Close. Temporal. So temporal lobes. And the last one?
Parental.
The parietal. So you've got the frontal, parietal, occipital, and temporal lobes. So what we're going to do is I brought with me a human brain.
Wait, did you do that? That sounds cute.
No, I took it from a 7th grader from last year who wasn't paying attention. And it, no, I'm just
Mine should be next.
You know, so where did this brain come from? So it turns out that when some people pass away, when they die, they donate their body to science so that we can learn. And so there was somebody in the Dallas community when they passed away said they were willing to donate their brain for education and research purposes. And so it's a gift that they give so that we can learn from it. So I have a brain from an adult who had passed away, who donated their body to science, so that you guys and us at the medical school can learn. So I'm going to show you the parts of the brain, and we're going to go through it together. So the question up front is, how big is a brain? Who can tell me how much the human brain weighs?
Oh, gross. Hey, that
No,
looks
this
like
is an
oatmeal.
adult brain.
That's small.
How much does it weigh? Less, 3 pounds. 3 pounds. So now, the human brain weighs 3 pounds. How much does a whale brain weigh? More than 3 pounds or less? More. It's about 8 times more. It weighs 20, 30, 40 pounds. Now, who can do more activities on planet Earth, a human or a whale? Humans, as far as we can tell, and there's still some research to be done, but as far as we know, we can create things, we can write things down, we can create technologies. And what's dripping is just water. We keep it moist so it doesn't get dry. Nothing else is dripping out. So the human brain only weighs 3 pounds, but the whale brain weighs 20 to 30 pounds. Why can this human brain be responsible for so many more functions when the whale brain is so much bigger? What do you think? Okay, so wait, let's first get an answer. What do you think? So you're right, the size of the brain correlates with the size of the animal, but the capabilities of the brain doesn't correlate with size. So what does it correlate with? It actually correlates with the number of neurons packed into that brain and how they talk to each other. So there are more neurons with more communications networked between them in a human brain than there is in a whale brain. And so even though the whale brain is so much bigger in size, the human brain can do a lot more different functions. And so what we're going to go through together are those functions relative to these lobes of the brain. Now, when I asked for the lobes of the brain, you guys told me there were 4. You said there was the frontal, parietal, occipital, and temporal. So let's go through and get you oriented. So this is the front of the brain, such that if this was in a skull, it'd be sitting just like this. So my brain right now is sitting just like this in my skull. So as I turn my head, it turns with me. As I go forward, it goes forward and back. And the front has which lobes of the brain? Frontal. Yeah, that's the easy question for the day. So these are the frontal lobes of the brain up front. Now, what do the frontal lobes do in the brain? What are they responsible for? So the frontal lobes are responsible for motor control. So moving your arms and legs come from the frontal lobes, and moving your mouth and your vocal cords, which we call what? Speaking. So speech. The frontal lobes are responsible for the creation of speech. And it turns out that this part of the brain right here is responsible for making speech. Such that if I were to cut this part of the brain out of a human, they wouldn't be able to talk. They would be awake. They would look at me. They would be able to run and jump and skip. But when it came time to speak, they wouldn't be able to produce a word. Okay, it would be very difficult for them to produce a single word. Now, this part of the brain in the frontal lobe is responsible for making speech. Yeah. They'd sit there and just look at you, and they may try to make some motions, but no vocalizations would come out. Now, a lot of times when there's damage to this part of the brain, it's incomplete. So if there's a lot of incomplete damage, this is what happens. I'll give you an example. If the sentence I wanted to say was, "That is a very pretty dog you have." If that was the sentence I wanted to say, but I had damaged this part of the brain, what would come out would be "very pretty dog." I wouldn't be able to get all the words out. It would be very difficult. It would be start and stop, and I would lose a lot of the language. I wouldn't be able to produce it. I would be able to understand what you were telling me. I just wouldn't be able to speak back in complete sentences. Yeah. That is a great question. So the question in the front is, does damage to this part of the brain cause stuttering? And the answer is no. Stuttering, it turns out, so lots of people have a stutter where it's some difficulty speaking. It turns out it actually has to do with how people hear language and hear their own voice. The production of speech is okay, but there's a circuit between hearing the language and speaking that gets interrupted in individuals with stuttering. And it brings up the question of where in the brain do you hear speech? So as I'm talking, I'm using my frontal lobe to create the speech. You're listening to me. Which part of your brain is being activated as those words get to your brain? And it's just behind it. It's right here in a part of the temporal and parietal lobe. And so if I damage this part, so if I damage the frontal part of the brain, what did I just tell you you have problems doing? Talking. If I damage this part further back, you have problems with what? So it turns out you can hear fine, you just can't understand what you hear. And here's the best example is, has anybody here ever traveled to a foreign country where they spoke a language you didn't speak?
Yes.
Where did you travel to? London? So I know that it's a different English.
Sorry, Paris.
Paris, there you go. So what language do they speak in Paris? French. Do you speak French? No. So when you would walk up into a store or into a house or into a restaurant and somebody says bonjour and they start speaking to you in French, you could just shake your head and nod, but you didn't understand what they were saying. If I were to take out this part of the brain, it would be as if you were perpetually in a foreign country. You would hear people speaking to you in English like I'm doing now. You wouldn't understand what they were saying. So the front part here controls the production of speech. The back part controls understanding speech. Now, we did a little test with the last couple of classes. I'll do it with you guys as well. So far, everyone's done a great job with this. I'm going to give you 2 sentences, and I want you to listen very carefully to 2 sentences and tell me the difference between sentence 1 and sentence number 2. Okay, you ready? All right, listen carefully. Here's sentence number 1. You are going to the store to buy oranges. All right, that's first sentence. Now I'm going to say sentence number 2. Listen carefully and tell me what the difference is. You're going to the store to buy oranges. Were the words in the sentences the same?
Yes.
Were the sequence of the words the same?
Yes.
Were they the same sentences?
Yes.
No. What's the difference between them? One's a question and one's a statement or command. So statement number 1 was, you're going to the store to buy oranges. That's a statement. Whereas you're going to the store to buy oranges, that's a question. How did your brain tell the difference? The tone of voice. So your human brain, this part of the brain, responds to what the words are. The exact same area in the other hemisphere allows you to interpret the tone of voice. So if I were to take out this part of the brain, it would be as if you're in France and you don't speak French. If I were to take out this part of the brain, you could understand the words, but you would never sense a question versus a statement versus sarcasm versus, because you guys are never sarcastic with each other, you wouldn't be able to understand the tone of voice. Okay? Yeah.
Isn't there something where someone can't understand tone of voice? Like
Yeah.
there's a disease or something?
There are lots of conditions that affect your ability to sense tone of voice. It's a sensory side, and it comes from the non-dominant side of the brain having changes in those cells. Yes?
When we're talking to ourselves, in our head,
Mm-hmm.
does that come from the brain? Or
Yeah, so you can think about language. You can think to yourself, and we've all done this. We've all sat there and said, I'm sure with this group, you've all sat there and said to yourself silently, I really need to study for my science test. I really want to learn this and learn it well. I'm sure you have that conversation with yourself every single day silently. That's a part of the brain where you're having the thought, but you're not activating the motor control. So you're thinking it, but you're not projecting it to the muscles of your throat, your vocal box to vocalize it. Because you can turn that off and just have the thought. Yes? How what? How that feels, yeah. So let's talk about that. So it's kind of a little squishy, kind of like, how styrofoam or those popcorn peanuts, you can squish them a little bit. It's kind of got that consistency, but it's important to know that this isn't what the brain, this isn't either the color or what the brain would feel like it was coming out of a live person. So when it's in the human, there's a little bit of pink, but it's a little grayer, and it's much squishier. It's closer, it's thicker than Jell-O, but kind of that side of things. You could really peel it apart a lot easier than this. When we take a brain out after somebody passes away, we put it in something called formaldehyde to get it a little stiffer so that we can handle it this way. And the formaldehyde gets all the proteins to stick together to give it this firmness, and it turns it this kind of brown color. Yeah.
When you're studying brains, do you put them in those jars with that has liquid, and then you just put them in there and they just float?
You can. So we do, when we take a brain out and we're using it for science, we'll put it either in a plastic or a glass jar with the formaldehyde in it so that it can fix the tissue. And then when we're ready, so if we're ever looking at the brain on the inside, we can then go through and actually do slices of it to look at the deep parts of the brain. So, yeah.
So how old is that? Did you pick it up?
This came out in the last 3 months.
Oh,
Yeah.
received that.
One hemisphere looks bigger than the other. Is that normal?
It's just how I'm holding it. These are, your hemispheres can be slightly different in size, but if I get these lined up, they're basically the same. Yeah.
If you're deaf, can you hear yourself think?
Say that again.
If you're deaf, can you hear yourself think?
So if you don't have, so if you don't have the ability to hear, everybody has a representation of a language. We all think in a language. And what's interesting is around language is you learn different languages as you grow, but depending on your age, it's easier or harder to learn a language. So this part of the brain, where you make and understand language, the front and the temporal parietal, those networks, those cellular connections are really forming as you're 1, 2, 3, 4, 5, 6, 7 years old, really on a high trajectory of forming lots of connections. It's easier to learn a new language as a 5-year-old than it is as a 10, 15, or 20-year-old. And so one of the languages, so if you are going to, who's going to be, you guys are 7th grade, in a year and a half, you'll be heading to high school. One of the languages taught at the high school is American Sign Language. So individuals who are deaf think about language in a slightly different way, but there is language. Yes? If you're, what?
Yeah.
If you don't have hearing, thoughts are not tied to the language we speak, whether it's sign language or whether it's speaking French or whether it's speaking English. Thought is thought. You just have a different representation of it. So if is anybody here bilingual, speak 2 languages really well? So for those of you who grew up in a household with 2 languages, have you ever dreamed in either language? Do you have a dream where there's English or a dream where there's the other language you speak? Has that ever happened? And so your brain can function in lots of different languages. All right, so let's get back to the parts of the brain just to walk you through them. So the frontal lobes were motor, speech, movement and speech. What does the occipital lobes do? So what was it? It's vision. And so as you are looking and seeing this brain, it is being received. It goes from your eyes through your optic nerves to the very back of the brain called the occipital lobes. So if I were to cut out an occipital lobe, what would happen? So that's right, you lose vision. Now here's the tricky part about it. So somebody earlier on, I think it was you, said the left part of the brain controls the right part of the body. Does everybody remember that?
Yeah.
It's the same thing with vision. The left occipital lobe is responsible for the right side of the world, not the right eyeball, the right side of the world. The right occipital lobe is responsible for the left world. So if I stand here, right in the middle of you guys, and I were to cut out my right occipital lobe, I would not be able to see these people. I would see you guys, but I could hear them. I would hear that they're there, but I could not see them. In order to see them, I would have to turn my head and get you on the right side of me. Yeah. Great. So the question was, what's the difference between your eye and your world? Here's the difference. So actually, if you want to volunteer, you're going to help me out with this. Come on up. Choose her question. We're going to have her go. So you're gonna tell everybody what the difference is. So I want you to stand here and face all them. And what I want you to do is, so look right towards the computer there, and I want you just to close your left eye. Keep your right eye open, close your left eye, all right? Now, can you see all these people off your right side? Okay, now what I want you to do is with your arm, keep looking straight ahead, but with your arm, move out to as far as you can see on the left. So your left eye's closed. So I'm gonna do it. You can. How far over?
I can't see.
Yeah, name some. Where's Ben? It's a great name. I'm Ben. All right. So okay, keep your eye closed. Keep looking straight ahead. Ben, raise your hand. All right. Now, open your left eye. Keep your head forward. Keep both eyes open. Now, who can you see past Ben? Without looking that way. Look straight ahead. You can see all the way over there. So the eyeball can see both sides of the world, right? You got all the way to Ben. Now, if I were to take out your occipital lobe, even with your left or right eye closed, you would lose everybody off the middle. So the lobe controls the side of the world. The eyeball can actually see both sides of the world. But why can't I see over here these last two folks with my left eye? Because my nose is in the way. It blocks my peripheral vision for that side. By occipital. If you didn't have a nose, you can see further over. Does that make sense? All right, you can. All right, yeah. All right. So we had a question about cross-eye. So you can, if those of you who can get your eyes to cross, all of a sudden your brain is seeing two images, not just one. And the brain doesn't like seeing two images of things. It prefers to see one. And we brought up the question of pain. So when you guys were studying the nervous system, you learned about neurons that control motor movement, right? Getting your muscles to move. And you learned about neurons that can control sensation, right? Give me an example of sensation. What does that mean? What does sensation mean? Feeling things. Like what? A what? An iron. What happens if you touch an iron? And it hurts. So you have. So what if I came through with a safety pin and started poking your skin? That would hurt, right? All right. So pain sensation. You guys can do this. Pain sensation goes from your body up to your parietal lobes. So frontal lobe was movement, occipital lobe was vision, parietal lobe is sensation. It's feeling the world around us. Now here's the fun trivia fact for the day. When I cut your skin, does it hurt?
Yes.
If I were to break your bone, would it hurt?
Yes.
If I were to cut into your brain, would it hurt?
No, you'd be dead.
No, but you're alive. If you're alive and I cut your brain, does it hurt?
Yes.
I don't know.
The answer is no. So let me explain. We can do surgery on the brain with people awake and talking to us, and we can cut into the brain while you're awake, and you will feel nothing. And the reason is those sensory neurons that get activated in your skin when you burn yourself or cut yourself, those sensory neurons that get activated when you break a bone, there are no sensory neurons in the brain.
Yeah.
There are no sensory fibers in the brain. So the brain is there to interpret sensations throughout the body. It can't feel anything. So you can do surgery on people who are awake. Yeah.
But when you cut through the tissue or bone right here, that will hurt.
That will hurt. So what we do is we numb up the skin and the bone. And what we'll do is we'll put somebody under anesthesia. We'll make them go to sleep while we go through the skin and the bone. And then once we're done with that, we wake them up. And as we're operating on the brain, they talk to us because we want to make sure we're not going to cut into anything that's really important. Because if we're getting close to the speech center, what we'll do as we're moving closer and closer is we'll say, hey, Ben, keep talking to me. And if they stop talking, we realize we're getting too close to the speech center. So we can do surgery on people and do it all the time while they're awake.
But then when
Yeah.
it's too late,
I'm sorry?
But then when it's too late and they stop talking.
Yeah, so the way we do it is instead of cutting, so I can take an electrode and I can put it on the brain and temporarily, for a split second, activate or deactivate the cells in their area so I know what they do. So if I put the electrode right here, the person's arm would fling up in the operating room. If I put the electrode right here, they would kick with their other leg. And if I put the electrode right here, they would stop speaking. So as I move that electrode around, they'll have different responses. Yeah. Yeah. All right. So did everyone hear that question? So if you have no sensory neurons in your brain, if it doesn't feel pain, why do we get headaches? Has anybody here ever had a headache? Yeah. So how many people here, when they got a headache, says your brain hurts? It's not your brain. So you get a headache when either the muscles around your skull are hurting, or the tissue around the brain, or the blood vessels around the brain that have sensory neurons can cause pain, but the brain itself doesn't hurt at all. So the question is, when you're doing surgery on the brain, how much of the skin and skull do you have to cut through? There are two different kinds of surgery we do on the brain. One of them requires a very small incision and then a small hole to be drilled through the skull about the size of a quarter. Another type of surgery needs us to make a bigger incision into the skin and take off a square of bone about the size, little smaller than an index card. And we can remove it, and then at the end, we put the bone back and fix it into place, and we sew up where the skin is. Yeah. Yeah. So if we were to stretch this out, so we have the top part, these convolutions on the brain that are called gyri. We have the divots, the deep things in between that are called sulci. These are not one continuous ribbon. What it is just outgrowths of cells. These are where the neurons live, the gray matter, the cortex of the brain is what makes up these gyri. And it's not one long ribbon that we can stretch out. Now, before we do a couple other questions, let me just get through one other thing for you. So we did the frontal lobes as movement and speech. We did the parietal lobes for sensation. We did the occipital lobes for vision. There's one other lobe we haven't talked about. Which one? The temporal lobe. All right, here we go. Ready? Here are the temporal lobes. I'm going to flip the brain over. This is the undersurface. These two tips right here, those are your temporal lobes. All right. So the frontal lobe did motor, the parietal lobe did sensation, the occipital lobe did vision. What do the temporal lobes do? Time. Not exactly. In a way, yes.
Do they allow you to move?
They don't allow you to move. That's frontal lobes are for movement. Yeah. Say it. Thoughts. So to a degree, yes, but one particular point of thoughts, they can play a role in whether or not you feel scared. They can play a role in how you perceive things. They can play a role in how you listen to things. And the biggest thing they do is help you form new memories. So if I walk into the room and introduce myself, and I say, hi, I'm Dr. Greenberg, and then I walk out of the room, and I wait a minute, and I walk back in and say, who am I? What are you going to say?
Dr. Greenberg.
The way you learned that was your temporal lobes. So what happens if I cut out your temporal lobes?
Short-term memory loss.
Short-term memory loss. And so as I come in and I say, I'm Dr. Greenberg, if I walk out of the room, even for just 30 seconds, if I were to cut out your temporal lobes, walk back in, you would say, who are you and what are you doing here? You wouldn't remember that you literally just met me. So we had an interesting conversation with the last group, I'll repeat it now, in terms of forming new memories. It turns out that you learn things, you form memories, you remember the facts for your math test and your science test and your English test and your theater lines and everything else. A lot of times you learn it while you're sleeping. And so it's important, we have found that the temporal lobes work better when people get enough sleep. So if you're going to bed late or getting up early and not getting enough sleep, it makes it harder for the temporal lobes to learn new memories. Now, how many people here, when they're studying for a test, like to take notes, like to write things down? All right? How many people here like to listen to a recording of something audio? How many people here like to watch a video, like a YouTube video to learn something new? All right. So you all learn differently. Some of you learn by writing, some of you learn by listening, some of you learn by watching. Everybody's brain forms new memories in different ways. Your temporal lobes forming connections with the parietal and occipital lobes allow you to learn in different ways. You have to find out what works best for you, because some of you will learn one way versus another, and there's nothing wrong with that. Each of us have developed slightly differently. All right, so we've done, yeah.
I have 2 questions. One is, so you know how like you said that when you're doing surgery and you're saying keep talking?
Mhm.
Like if they start talking too much, like and you don't like it, can you just like cut it out? So
Yeah, in general, that's frowned upon. So we don't cut it out.
Is it it's like a rule?
Yeah, we're not allowed to just to cut out because we're annoyed.
Have you thought about doing it?
No,
And also,
we take that part seriously.
the second one is like say, you know, like digits, is their brain, and you know Anthony Davis, would their brain be like the same size or
Okay.
be smaller?
So it's a good question. So everybody's a different height, weight. Does brain size change with height and weight? And to a degree, yes. And so there is an average weight of the human brain, which is 3 pounds, but some human brains are 2.5 pounds, some brains are 3.5 pounds, but it actually has 0 correlation with intelligence and what we can do. So it turns out the size and weight of the human brain doesn't dictate our skills or talents. It's how we form connections between the lobes. And I'll point out, you can change those connections through practicing. So if you wanted to learn a new skill or a new set of information, you have to teach your brain to do it. And your brain is capable, you just have to work it. Yeah. Yep, temporal lobe's right here.
So it doesn't matter.
So the question was, says, if you have a larger temporal lobe, are you better at remembering things? It turns out the answer is no.
No, like remembering more.
It turns out that the answer is no. Your memories are dictated by the cellular connections more so than the actual size and weight or inches of the temporal lobe. And so it's what's on the inside. Yes. So the question was, people with ALS, which stands for amyotrophic lateral sclerosis, has anybody here ever heard of Lou Gehrig's disease?
No.
No? So Lou Gehrig's disease, ALS, is a disease of the motor neurons in the frontal lobe and the motor neurons in the spinal cord. So if those motor neurons get damaged, what do you have problems with?
Walking.
Movement. Do you have problems with sensation? No. So you can feel things. Your thinking's fine, your hearing's fine, but getting your muscles to move are the problem. Because that's an example of a condition where a certain cell type gets damaged versus a lobe of the brain getting damaged. Yeah.
What happens if you swap brains with another person?
And I didn't hear that. Say again.
What happens if you swap brains with another person?
Yeah, the brain transplant. We have not perfected the brain transplant. When your brain comes out, that's it. It's over. You're not going to be used for classrooms. There's no way to transplant. Yeah.
Okay, so whenever you're younger, like whenever you get older, why don't we remember like when we were younger?
Okay. So how does memory work? So depending on it's an interesting question of how we store memories and what we remember versus what we don't. Because there are certain things we remember better than others. How many people here had an event that they felt was really frightening or scary and you remember it very clearly from years ago? All right. So it turned out that in setting of fear, when we get really anxious or afraid of something, the part of the brain, the cells in the temporal lobe, start to record more data about the event. So you remember it in more detail later on in life. How many people here remember what they had for lunch on August 15th? Right. So is what you had for lunch on August 15th a memorable event? You what? All right. So if you have the same lunch every single day, then that's cheating. But assuming you vary things up, certain things in life, the cells decide it's not important to remember forever what I had for lunch on August 15th, 2018. But certain events remember better. So those cells form connections. And it's those cellular connections that make the memory. So has anybody had a situation where you're asked a question? Maybe you're taking an exam and you read a question and you know the answer, but you just can't remember. And then after about 5 or 10 minutes, when you're thinking about something else, it just pops up. And you remember. You guys had that happen?
Yes, all the time.
So that has to do with how your brain retrieves memories. And we all store memories differently. So some of us store memories based on language. Some of us store memories based on visual cues. Some of us store memories based on sounds. For some people, has anyone here tried to memorize something for class by coming up with a rhyme or a mnemonic? So some people find that hard. Some people use it. So the way you access the memories depends on how you store them. Everybody's a little bit different. Yeah. It's a good question. We had it last time. When you have vision problems, is it a brain-based issue in the occipital lobes, or is it with the eyeballs? 99.999, almost always, it's with the eyeballs. It is very rare to have vision issues from the occipital lobes. It can happen, but it's very rare. Okay. Yeah. For you to be able to move your arm comes from the front. Any muscle movement is coming from the frontal side. Yeah. Oh, so that's an interesting question. How is the brain different when you're an extrovert versus an introvert? So being an introvert versus an extrovert is part of personality. It's part of all sorts of things that make us who we are. And that's a combination of both the decisions we make in social settings, and a lot of that's the frontal lobe and how the cells connect. And also it has to do with sensory cues. How many people here get really annoyed if somebody is chewing crunchy things next to them? It just really just can't. All right. How many people? All right. So we've got the people who get annoyed by sounds. How many people here have certain smells that they absolutely just kind of like certain foods cooking or bad breath doesn't count. All right. So something you don't want. So everybody connects certain sensations in different ways, and it drives our personalities and how we interact with the world. Some people prefer quieter places with less people, and they feel more comfortable. Other people like big crowds and being out there, and it has to do with how your brain interprets the world around you and then drives you to make certain decisions. So speaking of those decisions, we talked about the frontal lobes. So we talk about the frontal lobes for language and motor. Does anyone know what else frontal lobes do? We'll talk about one more thing. So the frontal lobes are the little voice inside of you that tells you if what you're doing is right or wrong. Has anybody here ever been in a situation where they said to themselves, I really shouldn't do that? And you either decided to go ahead with your mind. Okay. So when your inner voice says don't do it, it's the frontal lobes that dictate not doing it. Okay? And so if you damage the frontal lobes, you lose the ability to make those good choices in life.
Wait, so why?
It's possible. We can do testing later on and sort that out. It depends on making those choices.
I think
All right.
I did.
Okay.
Yeah. All right. So last part of the brain. You guys have done a great job. You got frontal lobes, parietal lobes, occipital lobes, temporal lobes. But when I was asking at the beginning about parts of the brain, somebody talked about a part of the brain that controls balance. You guys remember what part of the brain that was? Cerebellum. All right. Do you see this part here that I'm moving? You guys see that part? So this part with all these ridges, you're almost there, guys. This part with all these ridges, that's the cerebellum. That's responsible for balance. All right. You want to be my volunteer for the cerebellum? All right. We are going to test Josh's cerebellum. Are you ready? All right. I want you to put your left foot out. Put your arms out by your sides. And with your right hand, touch your nose. So that's his cerebellum is allowing him to maintain his balance. Now, whatever you do, don't move. All right? I'm going to push it. All right? Let's see if he can keep his balance. So as he feels me pushing him, he can laugh all at once. All right, good job. So as he feels me pushing him,
Guys.
he changes the control of the muscles. You saw him moving a little bit, but he didn't fall over. That control, that ability to change his muscle tone is coming from the cerebellum. It is the world's fastest supercomputer. It can take all the information about the world, information from sensation, him feeling how much I was pushing, information from vision, seeing where the walls and where the ground was, information from sensation about his muscles, incorporate it all at light speed, and then tell his muscles how to react so he doesn't lose his balance. And so that's how the cerebellum works. Yeah.
So what does the cerebellum do like when you spin around and get dizzy? Like what makes us like get off balance?
Yeah. So one of the cues that the cerebellum uses to control balance has to do with a structure in the inner ear called the semicircular canals. So it's a group of bones with some fluid in them in your ears that tell you where your head is moving. So as I move my head forward and back, left and right, the inner ear tells my cerebellum where my head is. So if I take Josh and I spin him around 20 times and I get that fluid in the inner ear moving really fast, when he stops, the fluid is still going. So his body is stopped, but his brain is getting a signal that the head is still spinning, so you feel dizzy. And when there's that mismatch between your body being stopped, but feeling like you're moving, you stumble and you're dizzy and you fall over because the inner ear is telling the cerebellum. Yeah.
I get sick really easily. Does that come from the cerebellum?
It comes from the inner ear. So for some people, when you spin around a lot, when you feel off balance, for some people it can trigger them to feel nauseous or even throw up. Yeah.
What happens if you, like cut half of your cerebellum?
So if you cut half the cerebellum, you have a lot of dizziness and imbalance issues because you're not getting all the information from both sides of the body. Yeah. Yeah. So we got this question a couple times. It's a good question. What happens in a concussion? So there are two different things that we think that can happen in concussion. So one is when there's a hit to the head, depending on where the hit is, you may damage a specific part of the brain. But what we think happens to most concussion recipients is when the brain is moving quickly, like you're running down the field or you're on your bike or whatever the case may be, and you fall and your brain all of a sudden comes to a stop. Going from fast to stop causes damage to some of the cells deep in the brain. And they can control balance, they can control movement, they can control a lot of things that lead to the symptoms of concussion. Whether it's memory issues, nausea, a feeling of movement, lots of people have different symptoms from concussion. Yeah. So that's a good question. So the question was about when you're born, does your brain look like this or is it smooth? When you're born, your brain actually looks like this. Your brain has the ridges, has the gyri and the sulci. It just gets bigger over time. Different species, so non-humans, can have smoother brains, and then there are certain genetic conditions that can affect a person's development where the brain can look smoother. But even an infant's brain will have these ridges, these convolutions on it. Yeah. So from person to person, the human brain will differ based on both size, so taller, bigger people have slightly bigger brains, but in general, the location of the gyri and the shape of the gyri are the same from human to human to human. So if I do pictures of the human brain, like an MRI or a CAT scan, everybody's movement center is basically in the same place. There can be slight differences, but in general, they're in the exact same place. Now, there's an exception to that, and that has to do with handedness and dominance. We're getting close to the end, so we'll get this in before the bell rings. How many people here are right-handed? All right, put your hands down. How many people here are left-handed? All right, now take a look around you. Left-handed, we've got 4 or 5 folks who are left-handed. So it turns out remember I said the frontal lobe is responsible, the frontal lobe is responsible for making speech. For right-handed individuals, it's your left frontal lobe that makes speech. For left-handed individuals, it's 50-50. Half of you, it's the right frontal lobe. So where your speech center is correlates with whether you're right or left-handed, between the left and the right brain. So if you're ambidextrous, it's a 50-50 split. Half of people who can use left and right, language is in the left, half of them it's in the right. So we do testing to figure out which side of the brain controls your language. Yeah, so the brain doesn't develop any emotions. That all happens in the periphery with the immune system. Yeah.
When you read, is it like your languages, or is it what you hear, or?
That is a great question. Did everyone hear that? So what is the difference between hearing and reading language? It has to do with the input. So in reading, you need the vision to capture the information and then to send it to this part of the brain to understand what you're reading. When you're hearing, it goes via a different pathway, but you need this part of the brain to understand it, whether it's written or spoken. Doesn't matter, you still need that same part of the brain. All right.
Are you?
Thank you.
All right. Thank you guys.
Oh, my God.
This was live streaming?